How has Antarctica's climate changed in the past? Is Antarctica being affected by global warming, and how might its temperature change in the future? What evidence is needed to respond to these questions? Global warming, another name for human-caused climate change, is a well-known problem. The quantities of greenhouse gases in the atmosphere, mainly carbon dioxide and methane, have increased due to human usage of fossil fuels like coal, oil, and natural gas, as well as agricultural practices, and are now much higher than pre-industrial levels. As greenhouse gases accumulate, more heat energy from the Earth's surface is held in the atmosphere rather than escaping to space, warming the atmosphere as a result. Our inability to completely appreciate the cascading impacts that the rise in greenhouse gases will have on other components of the climate system is a major contributing factor to the complexity of the global warming issue, such as the amount, rate, and pattern of warming. Of course, there are other factors affecting the climate of the Earth besides greenhouse gases. In addition, there are both natural and man-made differences in how the greenhouse gases themselves cycle between the atmosphere, land, and oceans over a range of periods. In conclusion, understanding and preparing for climate change requires far more work than it initially appears. Research on Antarctica, especially analysis of Antarctic ice cores, has been extremely helpful to our endeavor. As will be mentioned more below, the ice cores have allowed scientists to reconstruct past climate fluctuations spanning hundreds of thousands of years. We now have a lot better understanding than we did in the past of past climate variations brought on by natural sources, and this has provided us with critical context for assessing more recent human-caused changes. Some of the research stations covered in regional climate variation and weather provide essential weather data for predicting how the polar regions will respond to the increase in greenhouse gases. The polar regions are frequently referred to as the canary in the coal mine for detecting global warming. Furthermore, since 90% of the globe's ice is found in Antarctica, what happens there will have a big effect on the rest of the planet. The ice in Antarctica contains signs of previous climatic change. Antarctica's current weather did not always prevail. Fossils demonstrate that trees were present and covered most of Antarctica at various times during the continent's geological history when it was much warmer. These warm episodes for Antarctica occurred many millions of years ago as a result of many geological features and ocean circulation patterns. See the main sources of Antarctica's temperature. Since at least 6 million years ago, the majority of the continent has been covered under ice. Unlike the considerably older geological data, which dates back to about 800,000 years ago, the ice core record is significantly younger. The variations in Antarctic ice offer more insight into how the climate fluctuates under the current tectonic arrangement and how it might change in the near future because the distribution of land and sea has largely remained constant over this time. Ice cores are obtained by drilling cylinder-shaped chunks of ice out of a glacier or ice sheet. These ice chunks are the end product of thousands of years of snow accumulation, in which each year's snowfall buries earlier snow layers, which subsequently harden into glacier ice. Snow that fell at particular times in the past is used to create the layers of an ice core, and each layer serves as a time capsule by preserving information about the weather at those times. Ice cores are appealing because they can give us a wealth of knowledge about past climatic and environmental circumstances. Furthermore, the evidence has a high degree of dating accuracy and is consistent through time. Among the most important types of evidence and information are the stable isotope ratios of the oxygen and hydrogen that make up the layers of ice are used to reconstruct the air temperature at the time the snow fell. The thickness of the layers where annual layers of ice are visible indicates the previous annual snowfall totals. Evidence of how much wind erosion has historically taken place on continents can be seen in the amount of dust that has been preserved in ice layers, related to both the strength of winds and the levels of vegetation cover over the land in the past. Evidence of previous massive volcanic eruptions can be found in Tephra particles and the acidity of the ice. It is feasible to establish how these greenhouse gases have changed over time in the atmosphere by monitoring the levels of carbon dioxide and methane in the trapped air. The key idea of guiding the interpretation of stable isotopes in ice cores is that as air cools and condensation takes place, heavier isotopes of hydrogen and oxygen will condense out more quickly than lighter isotopes. Because the heavier isotopes of water vapor will become increasingly depleted as the air grows colder, when precipitation occurs, the water contributed to the ice sheet will be light, e.g. the ratios of 18O to 16O and 2H to 1H will be less. On the other hand, when the atmosphere over the ice sheet warms, the ratio of heavy to light isotopes will increase. These ratios are expressed as per mil instead of per percent and are calculated in relation to standard mean ocean water. SMOW. Because H2O with the lighter isotopes evaporates more quickly from the ocean, the isotope ratios of water vapor in the atmosphere and subsequently precipitation reaching an ice sheet are always negative in relation to SMOW. As an example, the West Antarctica bird ice core's oxygen isotope ratios range from -33 to -43. Since there is a shift of about 0.70/00 for every 1 degree Celsius change in the mean annual air temperature, the bird ice core displays temperature fluctuations on the order of 15 degrees Celsius during the previous 100,000 years. Ice and glacier cores have been extracted from several glaciers and ice sheets all over the world. Due to Greenland's higher snowfall rates than Antarctica, much of the groundbreaking research was carried out there, and the Greenland ice cores provide a more accurate record of change, with annual layer counting extending back to roughly 40,000 years ago. The oldest CO2 data, however, are contaminated by the presence of wind-borne carbonates from Canada in the ice, and Greenland's ice cores only stretch back around 100,000 years. There are 3 main regions in Antarctica where long ice cores have been found. In the Dome Sea region of East Antarctica, the EPICA team obtained the ice core with the longest record, stretching back over 800,000 years, European project for ice coring in Antarctica. At a depth of 3,270 meters, the coring in the ice was completed in 2004. In the 1990s, a different substantial core, again from the Vostok station in East Antarctica, was studied. The Vostok ice core contains information on the climate going back about 400,000 years. West Antarctica is represented by the bird ice core record, which was drilled to a depth of 2037 meters. According to research using stable isotopes, the Quaternary Ice Age's glacial and interglacial cycles, which caused natural climate variations, are responsible for the long-term temperature changes in Antarctica. The cold, glacial stages often last much longer than the mild, interglacial periods, which span for around 10,000 years. Our current interglacial has so far lasted for 11,700 years. Be aware that the EPICA figure indicates that the amplitude of warm/cold oscillations rose around 400,000 years ago. These cycles led to substantial shifts in sea level in addition to major variations in temperature. During the last glacial maximum, sea level was approximately 120 m lower than it is today. These differences in the overall amount of ice on land were the source of these sea level shifts, both in the northern hemisphere and in Antarctica. Importantly, changes in temperature closely track changes in the concentrations of carbon dioxide and other greenhouse gases. While the timing of these natural climatic variations is determined by periodic changes in the Earth's orbit, Milankovitch cycles, variations in greenhouse gas concentrations have a critical role in worsening the early temperature swings. In other words, the amount of greenhouse gases in the atmosphere increased the size of the temperature variations compared to what they would have been without them, in addition to reacting to the orbitally caused temperature swings. This offers compelling evidence that modifying the concentration of greenhouse gases in the atmosphere, as we are now doing, will affect the planet's temperature. Because of its greater area, greater height, and greater grounding level, the East Antarctic ice sheet is less vulnerable to climate change. It's even conceivable that warmer temperatures could lead to a greater positive mass balance and a thickening of the EAIS because of increased interior snowfall. How much Antarctica will ultimately contribute to the rise in sea level over the next century is yet unknown, although this is a contentious issue. That was for today. Thank you for staying with us. Don't forget to like our video and subscribe to our channel.